Hello everyone, welcome to Coffee with Caleffi. Today we are talking about pressure reducing valves. This is kind of a big push topic for us this month. We have a lot of different resources related to this. And this episode of Coffee with Caleffi kind of dovetails with an hydronics that we just released as well. So to get started, we'll go through a couple housekeeping slides and then we'll turn it over to our presenters today. So if you have issues with your audio, here are a couple things to do. Usually the best course of action is just to restart GoToWebinar to quit and join again, but there is a tech support line directly to GoToWebinar if you're having kind of long-term issues there. If you hit yes at the end of the presentation in the post-webinar survey, we'll send you a copy of the presentation, and then it will also be archived on YouTube with the rest of our videos from Coffee with Caleffi and other series things that we have at Caleffi. Okay, go to the next slide. Certificate of attendance. So this will be emailed to you after the class, and you can report this to your state or your whoever is keeping track of your CEUs. Sometimes they take them, sometimes they don't, but we at least give you the certificate to self-report if that is acceptable for your group. Okay, and then the Legio mix, we always like to bring this slide up during Coffee with Caleffi. This group of plumbing components won a finalist, one of 3 awards at this year's AHR Innovation Awards, the Legio mix, the sink mixer, and the thermosetter. So we've got a lot of great videos about these products as well in our archive. And then this is kind of just released digitally and is at the printer right now. So people that have signed up to get a hard copy in the mail, these are being printed right now. We'll ship them out to all of you that have signed up there. We also have on the next slide, we have this as a digital version as well. So you can download a PDF like we've always had, but the newer editions, including this one on pressure reducing valves, you can go to hydronics.caleffi.com, and it's a little bit more rich media. You can see videos that relate to the topic. You can click on some more hyperlinks that wouldn't be available with a static PDF. So that's another great way to check out hydronics. So next month, we're going to be back talking about expansion tanks for both plumbing and heating applications. And we've got 2 Caleffi trainers, Hot Rod Rohr and Cody Mack, are going to be covering that topic. This is something that comes up all the time, something that we get calls on the tech support lines that relate to this, and kind of the adjacent issues that improper piping or expansion tank location or things like that can bring up. So tune in next month for that. And today we have 2 presenters. So we're going to start with John Siegenthaler. He is the principal of Appropriate Designs and is a regular contributor to Coffee with Caleffi. He's probably by far the host externally with the most different hosting role appearances over the years with Coffee with Caleffi. So we're glad to have John Siegenthaler back with us. And then Kevin Freidt is our Director of Product Management and Technical Support at Caleffi North America. He's going to cover kind of the second half of the presentation with some slides that relate to applications. So we'll get started with John Siegenthaler. I'll turn it over to you.
Well, thanks, Max, and folks, glad to be here. We've got a nice presentation put together about a product here that Caleffi has a lot of experience with. What I'm going to do is take you through the basics of pressure regulation in plumbing systems. What are some of the issues of both, especially excessive pressure, since we're talking about pressure reduction. We'll look at a little bit at the physics, what's involved with, excuse me, with both static and dynamic pressure. We're going to look at 2 different designs of pressure reducing valves. For smaller applications, typically a diaphragm type valve, and then for larger applications or for higher pressure applications, a piston type valve. As with any valve, they're going to perform best when they are sized properly. So we'll take a look at what are the sizing criteria. And then we're going to look at some unique applications. One of those is a 2-stage pressure reduction when we have a very high starting pressure, like at the bottom of Hoover Dam, trying to take a pressure at that level, several hundred PSI, and bring it down to something that would be suitable for a building, we need to use a two-stage pressure reduction technique. And we're also going to look at putting two pressure reducing valves in parallel. And that's useful when we need a wide range of flow rates. These are reliable products, but we are going to look at some common troubleshooting techniques. Excuse me. Most of those are just, for example, dirt in the fluid. How do you disassemble the valve, clean it, put it back in service? And then I'm going to hand it over to Kevin. He's going to talk about some applications in both smaller buildings as well as some high-rise buildings. And then we'll do some questions. So excessive water pressure, I'm sure all of us at one time or another been in a bathroom and turned on the water only to find the water spraying up out of the sink, spraying on the counter, probably spraying up on your clothing. That can happen depending on what the pressure is and the design of the fixture. And of course, in a shower, you know, we can have low pressure where the shower head doesn't perform well, but we can also have excessively high pressure in a shower, and literally pressure to the point where the water doesn't feel very good when it hits you. Some of the other issues that some of you perhaps have experienced, hoses, especially as they age, high water pressure can eventually cause leaks in a hose. If that's outside on a lawn, like you see here, that's, you know, you're going to lose some water. But if it happens to be a washing machine hose, that actually is one of the higher incidents of insurance claims. When a washing machine hose, especially a low-cost hose that's aged, you can see it's getting kind of an aneurysm, so to speak, in it. And if that bursts and nobody's around, that can cause a lot of damage. So we want to be able to control water pressure, typically no higher than about 80 PSI in an application. Another cause of high pressure is changes in elevation. Now, this is a shot out in Colorado. It just shows a housing development here, and it, you know, there's several hundred feet of elevation change, and that can cause wide variations of pressure, especially if we start with roughly atmospheric pressure at the top of that hill and a pipe goes down through that hill. We can calculate, and we're going to do that shortly. We can calculate how high that static pressure can become as we go down the hill. And in round numbers, for every 100 feet of elevation change, the static pressure in the pipe, the pressure in the pipe when there's no flow, is going to change by about 43 PSI. So depending on which way the water is moving from its source, if we're going up from downhill, you can see the pressure decreasing there from about 83 at some reference elevation to about 40 when we're 100 feet higher. Or if the water source is up on a hill and we're starting at whatever pressure, as we go down every 100 feet, we're going to actually be adding about 43 pounds per square inch. So that's another source. In the Midwest or any area where you have relatively flat terrain, many of the municipal water systems have these towers, water reservoirs, and again, depending on the height difference between the water level in that reservoir, in that upper tank, and that looks to be at least 100 feet there. It could be more. You're going to have a buildup of pressure down below. Okay. New York City, if you look at the skyline, I'm sure many of you have seen these tanks. Some of these are for fire protection systems, but some of them are also for potable water systems. And these are not pressurized tanks. They're essentially cisterns up on a roof. And just to give you an idea, if we started with a building with a tower up on a roof like this, and let's say the water level in the tower is roughly 30 feet above the roof line, as we go down, and this example just shows 10-foot story heights, for every 10 feet, we're adding roughly about 4.3 PSI. So even though those pressures near the top are relatively low, as we go farther and farther down, eventually we get to a point where we have excessive water pressure in the building, and a pressure reduction valve would be suitable there. Now, going the other direction, this is more common today where we have a high-rise building, and perhaps a building that's even 1,000 feet or more tall, how do you get water to go up through there? Well, if you just do the math quickly, you would need, for 1,000 feet of lift, you would need 433 PSI, way beyond what you want to run a plumbing system at. So typically what is done is to use a series of booster pumps. And the photo there shows a redundant pumping system. And these pumps essentially would run 24/7. They have some inlet pressure. And if we start down at the bottom here at roughly 60 PSI coming in from the street, we're boosting to 155 PSI coming off of that first pressure boosting station. So again, we would have water in the riser that is well above the pressure that we would want to have at fixtures at that level in the building. So pressure reduction valves can be used there. And Kevin will show you some unique applications where you can use pressure reducing valves on every story, or you might group together 4 or 5 stories to a set of pressure reduction valves. And there are trade-offs either way, and he'll get into that. But if you take a look at this graphic on the right, you can see eventually, as we go up from that first pressure boosting pump, we get back down to some other pressure, let's say 60 PSI, and the next booster pump just pumps it up to a higher pressure, and the same scenario repeats, where the floors that are just above the pressure boosting pump are going to have a pressure reduction valve system to, again, keep those pressures within a normal range. So the physics is pretty simple here. We divide water pressure in a plumbing system up into 2 different categories: static, meaning when the water is not moving, and dynamic. And the word dynamic implies motion of the water. So we'll start with static pressure. If we have a horizontal pipe, and on the left side here, I'm showing a pressure gauge with 30 PSI. If it's a horizontal pipe, the water's not moving, the pressure would be the same anywhere along that horizontal pipe, regardless of the pipe size, how long it is. There's just not going to be any change because there's no change in elevation. Now, next one down, if we have a sloping pipe and we start at 30 PSI up at the top, and as we come down 10 feet, 10 times 0.43 would tell us the increase in pressure. So we're up again by about 4.3 PSI over where we started. And if we go in the other direction, same concept, except we're subtracting. So starting at 30 PSI, going uphill by 10 feet, we subtract 10 feet times 0.43. The number 0.43, that's typical for cold water. That number will vary slightly with the density of water, but typically in a plumbing system, we use 60-degree water as a reference condition for density. Now, when we start to mix motion into the picture, we have to account for the fact that as water moves through a plumbing system, there's going to be friction. And as we move down the pipe, we can calculate what the reduction in pressure is. As friction dissipates mechanical energy away from water, it manifests itself as a drop in pressure. So again, we'll start with a horizontal pipe. Now, there would not be any change in static pressure along this horizontal pipe, but let's say we've done a calculation, and there are tables for this, there's charts, there's software, and at a certain flow rate, a certain pipe size, and a certain length, let's say we've dropped by 3.5 PSI. And again, that's a loss due to the friction as the water's moving through the pipe. We just subtract that from where we started, we're at 26.5 PSI. Now, when the water stops moving, let's say there's a fixture at the end, a valve of some sort, when we stop that, that 26.5 right here would go right back to 30 because we'd be returning from a dynamic condition to a static condition. Now, as we go downhill, same thing with static pressure, we would be adding 0.43 times 10, but we also have to subtract the loss due to friction. That loss is always going to be there regardless of the direction of the flow in the pipe, up, down, horizontal, at an angle. That really doesn't matter as far as dynamic pressure loss is concerned. So we basically break it up into a calculation for what's the change in static pressure, and then we correct for the loss in dynamic pressure due to friction. And the formula for that, pretty simple. We can figure out the pressure at some point, the static pressure at some point in a piping system. If we know the pressure at any other location in that piping system, and again, the water in the entire system assumed to be stationary, we add 0.43 times the height difference in feet if we're going down from that reference location, or we subtract 0.43 times the number of feet if we are going upward. So that's a pretty simple formula to deal with. Now, moving on, what's happening inside a pressure reducing valve? This is a very simplified diagram, but it shows the basic idea. Like any valve, we've got a shaft, we've got a disc and some type of a sealing element here. The higher pressure water would be coming in from the left, and the reduced pressure water would be leaving the valve over here on the right. And right now, the valve is shown in the closed position. There's no flow from the inlet to the outlet. Now, there's two forces at work here. There is a spring in the pressure reducing valve, and that spring is going to create a downward force against a flexible diaphragm. Okay, and this diaphragm will move up and down depending upon the spring force, and then opposing the spring force, if you see right here on the outlet side, there's a little port that essentially communicates the outlet pressure to the area under the diaphragm. So pressure times area is force. That's the upward force counteracting the force created by the spring. If the force created by the pressure here is higher than the spring force, it's going to drive the shaft upward, and that's going to eventually close off that valve, and vice versa. If the pressure against the diaphragm is reduced, which would happen when a fixture starts to draw water on the outlet side of the valve, then the spring force is going to be the dominant force. It's going to push the shaft downward, and it's going to allow some flow to go through the valve. So fundamentally, it is an upward pressure force created by the downstream water pressure that is being opposed by the spring force. And up at the top, just again, a simplified concept, there is some type of a threaded adjustment. I'm just showing a screw here. If we turn that screw down, we will compress that spring and create a greater force. So we would be increasing the pressure rating, or I should say the pressure setting of the valve by turning the screw down, and vice versa. So over here on the right, here's an application, or just the same concept, same valve cross section. And you can see the upward force on the diaphragm here is assumed to be reduced because the water pressure in the downstream direction has gone down. Somebody perhaps has opened a fixture. The spring now becomes the dominant force that pushes the shaft downward, and you can see flow can come down around the seat of the valve and go through the outlet. So again, it's a very simple concept. Now, the concepts I'm showing in these cross sections have been refined, and you'll see a couple examples of Caleffi pressure reducing valves down here. Refined in the sense of reducing pressure losses going through the valve, refined in the sense of allowing a valve that can be disassembled. So if there is dirt that comes into the valve, it can be cleaned up, it can be serviced. The pressure gauge shows you the downstream pressure, and of course there's an arrow on the valve. Always look at any valve for an arrow, make sure it gets set in the right direction or installed in the right direction. And then depending on the model, there are pressure settings. So the calibration of the spring force against the diaphragm force has been predetermined, and it's actually built into a number system that is on the valve, and you basically set it for the downstream pressure and it takes it from there. So no electricity, just basic mechanical forces involved here. There is another type of pressure reducing valve design. It's based on a piston. So essentially what we're doing is we're replacing the flexible diaphragm as the element that moves with a piston. And this is similar in concept to a piston and an engine. It's a precisely machined metal piston. You see the O-rings that seal it to the cylinder walls. And again, you'll see the inlet port here for the downstream pressure, which would create an upward force against the piston versus the downward force coming from the spring. And this type of valve is a little more robust. It can handle higher pressures than the diaphragm type valve. This is used a lot in irrigation systems. It's also a good one to help minimize any potential for water hammer. So in the cutaway here, you can see a little bit of the piston here. You see the inlet screen that protects against debris getting into the seat of the valve. And basically above the piston here, you can see the spring assembly and the adjustment screw up at the top there. Again, turning that down would increase the setting pressure of the valve. So both Caleffi offers both types of valves. Any valve that has water flowing through it is going to create a pressure drop to some degree. This is true in any kind of hydronic system. It's true in valves that are designed for plumbing. And the theoretically ideal valve would not have that pressure drop. You would set it for perhaps, let's say 60 PSI, and regardless of the flow going through it, it would stay right there at 60 PSI. Well, you really can't have a valve like that. It just can't be done. So any valve has what is called a fall off pressure, and it's simply the loss in pressure due to the friction, the turbulence of the flow as it goes through the valve. Over here on the right, there's a chart, and it's a comparative chart with different products that are on the market. And the green curve there represents a 3/4 inch pipe-sized Caleffi 535 valve. And you see there is some fall off. All the valves start, let's say they were set at, I'll say roughly 75 PSI. When there's minor flow going through the valve, the fall off is very minimal, and all these valves have fairly comparable performance. But as we start to increase the flow rate, and the graph here down at the bottom, it represents, for example, a bathroom, a lavatory in a bathroom, lavatory plus a shower in operation at the same time, and then adding a dishwasher in or some other appliance. So as we move from left to right, you can see that all the valves are dropping in their outlet pressure, but the Caleffi valve there has the least fall off. So we'll continue to talk about fall off pressure as we start to look at the design of valves, especially valves in parallel and series. Now, sizing is fairly simple. The Caleffi pressure reducing valves are basically designed so that they can handle flow velocities between 3 and 6 feet per second. And you can see on the graph right up here that range is mapped out. And then down at the bottom, a typical range of flow rates, recommended flow rates for different pipe size valves. So for example, a 3/4 inch valve would handle anything down to about 7 gallons per minute and up to about 12.5 gallons per minute. Now, occasionally you'll have flow rate ranges that are wider than what a single valve could accommodate. And that's where we're going to get into putting two of these, two different size pressure reducing valves into a parallel configuration. It's a very interesting and a very a neat design from an engineering standpoint, how one valve will handle the lower flow rate range and then automatically transition to the larger valve as the flow rate range increases. So keep in mind 3 to 6 feet per second, and basically using this reference table as a guideline when you're selecting the valve. And also keep in mind that the valve size may not, in some applications, may not be the same as the pipe size. It might be possible, for example, to use a 3/4 inch pressure reducing valve, even though the pipe size is 1 inch. So we don't want to size pressure reducing valves by pipe size. In other words, if we see a 1 inch pipe, we don't want to automatically assume that a 1 inch pipe size valve is the correct size. Stick with the chart and the 3 to 6 feet per second. Another performance index that we talk about with pressure reducing valves is pressure reduction ratio. And it's a very simple idea. What is your maximum inlet pressure? And divide that by the minimum outlet pressure, okay? Pressure reducing valves have to be applied within a range of pressure reduction. We can't expect any pressure reducing valve to start with, as an example, 150 psi and take that all the way down to 15 psi in a single valve. It's possible to do that with other valve combinations, but that would be a very wide ratio. So as a rule of thumb, a pressure reduction ratio of 2 to 1, starting with the upper pressure. So for example, we start at 150 psi, taking that down to half, or a pressure reduction ratio of 2 to 1, we'd be down to 75 psi. Those are typically no problem. It is possible to go a little higher than 2.1 up to about 3.1, but that 3.1 is a hard stop. Don't exceed that. And we'll talk about what'll happen if you do that. Basically, you're asking the valve to do something it just isn't designed to do. So if we get into excessive pressure reduction, one of the things that can happen in the valve is cavitation. And cavitation, we've talked about this in other webinars. Cavitation is where we get the pressure in the water low enough that the liquid water will actually flash to a vapor. And typically in the hydronics industry, we talk about this in connection with circulators. At the eye of the impeller, if the pressure drops below the vapor pressure of the fluid, that fluid will instantly change from a liquid to a vapor. And this can happen in a pressure reduction valve. And just to show you what's going on, here's that same graphic we looked at earlier. And down below it is a chart. And this just shows representative pressures. And when we talk about cavitation, we're talking about absolute pressures, okay, with an absolute vacuum as zero pressure. So we have some pressure at the inlet. And as the water starts to travel through the valve, again, there's turbulence, there's friction, and we start to get a pressure drop. And you can see that pressure drop becomes very significant as the water goes through, I'll call it the throat or the seat of the valve. That is the most constricted area in the valve. It's the area where you have the highest turbulence, the highest friction, and the pressure can drop down. And then as the water starts to kind of convene back together from its passage through that zone, the pressure goes up a bit. Now, down below here, we've plotted a couple lines. The red dashed line is the vapor pressure for hot water. Let's say water at 120 to 140 degrees Fahrenheit. As the temperature of the water goes up, so does its vapor pressure, okay? And then the blue line would be the vapor pressure for cold water. Now, we don't want this orange curve to hit either of those lines. So we'd like to have a safety margin right here. If we were working with hot water, for example, we want to have a safety margin where that minimum pressure at the seat of the valve when it's operating is still above the vapor pressure of the hot water. And that's how we avoid cavitation. It's very similar to the concept of avoiding cavitation in a circulator. We don't want that pressure at the eye of the impeller to drop down to the vapor pressure. So what do we do when we're dealing with really high pressures? I showed a photo there of Hoover Dam. I don't know exactly how tall that dam is, but let's say there's 250 psi at the bottom of that dam, and maybe somewhere's down there's a fixture, and we want 40 psi water at that fixture. How do we deal with such a high pressure reduction ratio? And one of the common solutions is to deal with two-stage pressure reduction. And it's, again, a pretty simple idea. We're going to use two valves in series. And just as an example, here's a PistonType Caleffi 536 pressure reducing valve. We're starting with 250 psi over here on the left. And that can take down to, let's say, 115. Let's say we set that so our gauge is reading 115 psi. So there's a pressure reduction ratio of 2.17. Again, a little higher than 2 to 1, but definitely lower than 3 to 1. So that's a very acceptable pressure reduction ratio. And then the second valve, a 535, is taking the 115 and reducing it down to 60. And again, these are maximum pressures, okay? So 115/60, just under a 2.1 pressure reduction ratio. So here's a photograph. Typically, you want to keep these valves quite close together, minimize the amount of fluid in between the valves here. So that's one way to do pressure reduction. In theory, we could go to more valves in series, but for most building applications, 2 valves in series and looking at the overall range that these valves can handle, usually it's not necessary to use more than 2 to 1. Okay, so 2-stage pressure reduction. All right. So I'm going to turn it back to Max. We've got a poll question here.
Okay, so I'll launch that there. So in the context of very high pressure, have you ever designed a system, sold it, designed it, installed it with 2 PRVs in series for 2-stage pressure reduction? So we've got an often, occasionally, or never answer. And then if you want to, as well, you can put, what was that application if you answered often or occasionally in the poll. You can throw that into the chat and we can read a couple of those if they come in. But yeah, we just are interested to see where this comes up. There are some examples that Siggy gave were high-rise construction or mountain locations. We know that we've had some kind of consulting with some weird applications in the mountain states, and not even in Colorado and Utah, but even in North Carolina, where it seems like high pressure was an issue that they were always dealing with. So I'll give that another couple seconds here. Okay, so I'll read these for you, Siggy, in case you can't see them. So often was only 3%, occasionally 25%, and never was 72%. So that's kind of an interesting look at that. And we'll kind of talk about some of the things in the troubleshooting section that maybe it could be a good fix in the future. So I'll turn it back over to you.
Yeah, and quite honestly, it's interesting. I've never previously thought a lot about using multiple valves to broaden either the pressure reduction ratio or using a wider flow rate ratio. So these are some techniques that are definitely useful for designers. Okay, let's go back here. Now, the other situation that you can find is that oftentimes you may have a very wide range of flow rates over which we want to regulate pressure. And using 2 PRVs in parallel allows us to do that. So here's a photo. That's a larger valve up at the top, probably 1.25 inches perhaps, and then a smaller valve down at the bottom. And you'll see both valves have isolation. That's important because these valves are serviceable. They have inlet screens. And if they do accumulate dirt over time, we do want a way to isolate the valves so we can unscrew the top and clean out that inlet screen, okay? So let's say we've got a requirement here, a little maybe hard to see it. Let's say our flow requirement is from 3 gallons per minute up to 33. And we want to maintain an outlet pressure somewhere in the range of 50 to 70 PSI. So how do we do that? Well, again, 2 valves in parallel. Let's start with this graph. And what we're looking at is the outlet pressure, where the outlet T is, where these 2 valves come together. And if we start at 0 flow and we've got the valve set at 70 PSI, this valve will be the first one to become active. As the flow starts to pass through there, you can see, again, there is some fall off in pressure due to flow going through the valve. The upper valve, I should point out, is actually set at 60 PSI. All right, now the lower valve is set for 70 PSI. So the upper valve here that is grayed out isn't doing anything initially. There's no flow going through it. So the lower valve, a smaller valve, is handling this portion of the flow rate range. And once we get down to about 60 PSI, and again, that's a fall off of about 10 PSI, it looks in this application to occur, I'll say somewhere between 12 and 13 gallons per minute of flow. Now the upper valve starts to become active and the lower valve actually starts to become inactive. So we're basically handing flow or pressure regulation rather from the smaller valve to the larger valve at that point. And the larger valve, again, will experience some fall off as our flow rate goes out. But if we get all the way up to, let's say, 32 gallons per minute, we're still at 53 pounds per square inch outlet pressure, which is within our spec here. And it is possible, we've seen applications where there's more than two. They would typically be, they would vary over quite a size range. The smaller valve handling the lower flow rate. Then as we go to higher and higher flow rates, essentially we're handing pressure regulation off to larger and larger valves. So again, two valves in series to handle a wide pressure reduction ratio, and two valves in parallel to handle a wide flow rate ratio. And I've got just a very quick section here on troubleshooting. There isn't a lot that is wrong with these valves. They're reliable, but given the plumbing system they're installed in, there could be things like dirt. So let's say one of the symptoms we're noticing in an application is downstream pressure slowly increasing over time. That is typically going to be dirt, even small particles that are accumulating between the disc and the seat of the valve. And that is a serviceable situation. You'll see the hex flats on the upper assembly of this valve. You can disassemble the valve and simply take a toothbrush and just gently clean that dirt off. You don't want to be highly aggressive on there. Don't put it on a wire wheel and cause scratches in it because, again, that's a precision machine surface. Clean it up, put it back together again, and that should take care of that situation. Now, another symptom might be flow to all the fixtures downstream of the pressure reducing valve decreases over time. Now it's a situation where it's likely dirt on the inlet screen of the valve, and all these Caleffi valves have this stainless steel inlet screen. And there's an example of the valve actuator assembly that's been removed from the brass body, and you can see the screen and you can see the dirt that's accumulated on the screen. And this is just going to cause more and more interference with the normal functioning, the design function of the valve. So again, get the old toothbrush out, water, some detergent, and just gently clean that off and put that actuator assembly back in. That should take care of it. So both of these troubleshooting instances are essentially just not something that's gone wrong with the valve. It's simply how has the valve dealt with dirt that's in the system. If you're going to have a persistent problem with dirt, it would be a good idea to have a Y strainer that's rated for potable water as a separating device upstream of the pressure reducing valve, simply to expedite keeping the inlet screen of that valve relatively free of that debris, cleaning it at the Y strainer as opposed to taking the pressure reducing valve apart each time dirt has to be removed. Okay. And we have one more here. Actually, two more. The PRV is making noise or chattering during periods of low demand. Okay. This will happen if the valve is oversized for the flow rate. And remember, we talked about that flow rate range for the different sizes of valves. If the valve is oversized, it's going to hunt. It's not capable of stabilizing at very, very low flow rates. So you're going to get a situation where it's going to allow some water to go through, and then it's going to shut, and then it's going to open again, it's going to shut. So you're going to get a chattering sound, a vibration from the valve. That's symptomatic, again, of the valve being oversized. So the correction on that is to select, again, based on that chart, keeping in mind that you don't just look at the pipe size and say, you know, if it's 1.5 inch pipe, I need 1.5 inch valve. Size it based on that flow rate range that it's designed for. Okay. And finally, when we have noise, high-pitched sounds coming from the valve, that's typical of excessive velocity, and that can happen if the valve is undersized. Okay. And you might say, well, how could that happen? Let's say I sized the valve correctly. Well, maybe you did initially, but if the building was expanded and more fixtures were added downstream of the point where the PRV is located, you're asking it to handle more flow. and that again could cause that noise. So if that's the case, you may have to replace that with a larger PRV, again based on the 3 to 6 feet per second flow rate range. Okay, and then we have one more poll, and then we're handing off to Kevin.
Okay, I'll go ahead and launch that one. So have you ever used 2 PRVs in parallel to stabilize wide water pressure over a wide range of flow rates? Often, occasionally, or never. And we had a question come in about this too, is, you know, how do you size this? So I'll just kind of look at the chart and kind of talk through a scenario that maybe your low end is somewhere around 2 GPM, but your high end is 50. So in that sizing chart, you could see that maybe a 2-inch valve is going to cover your top end all the way up to that 45, 50. But you might need to add a 1-inch further, you know, in parallel in order to hit that proper stable outlet pressure for the low end, where it would kind of fall off the end of the 2-inch valve there. So probably not one specific way to do it, but that chart with the blue band where you can see the 3 to 6 feet per second would be where you would look to kind of figure that out based on your project. So let me close the poll and I'll share those results. Okay, so parallel PRVs, we had 11% often, we had 23% occasionally, and then we had 67% never. So a little bit higher, you know, market share as far as more dual PRVs used in parallel than in series is kind of what I see with that, I guess.
Okay. All right, now we're going to hand it over to Kevin, and he's going to talk about applications.
Okay, thanks, Max. Thanks, John. Stay handy in case you have any questions or comments as we go through this. So we're going to take a look at some application schematics that will show us where PRVs are typically installed in different size buildings. And this one is a low-rise residential building. So if you go look at the bottom of the slide, you can see the supply point where it's coming in. That might be the municipal water line coming into the basement of a 2-story house, for example. And we have one single PRV in the cold water inlet, and that one serves the whole house. So that cold line will go over to in this example, we have an indirect water heater and a thermostatic mixing valve there. You can see the blue line serves the storage tank and the thermostatic mixing valve. And then the hot or tempered water will go up the riser and serve the main floor bathrooms and laundry room and kitchen and on up to the second floor. So if you remember what John was talking about with static pressure, say we had that PRV set at 45, maybe up in that upper bathroom, that pressure would be a little bit less due to the static. And then it would be even less too when you consider the dynamic pressure losses in this residential application. So this is a simple picture that is very common. I don't have a PRV in my home because the municipal supply is well regulated. Do you, John? Do you have a PRV at your house?
No, we have a well pump running between 30 and 50. So again, kind of self-regulated.
Okay, so again, this is a very simple application. So a single PRV would serve for this residential application. Moving on. So the purpose of this slide and the next couple of slides with schematics is to illustrate, what John was talking about with static pressure principles. This is a very simple schematic, but what we're looking at here is 7 floors and a single PRV. So down at the bottom, if we have our main supply at 70 PSI coming in, what we'll do is put in one PRV to serve the bottom few floors. So if we set that PRV at 45, you can see that the floor 0, the bottom would be 45. And as we go up in elevation, we're going to just assume 5 PSI just to simplify the math here. So 5 PSI is a little bit less than 12 feet between floors, and that just makes it a little easier. So as we go up in elevation, you'll see that the downstream pressure of the valve would decrease by 5 until you get to a point where it's too low. Actually, that floor 4 with 25, that's a little bit on the low range. So that may or may not be acceptable depending on the designer. But what you can do before the PRV is come off that main line and go directly up to, for example, floor 5. So again, with those static pressure principles, if we went up from floor 0 to floor 5, if our line coming in was at 70, we'd have 45 PSI up on floor 5. And then it decreases as you go higher. So again, just illustrating the static pressure principles. And this is a very simple system, and you could do it with one PRV, depending on how you piped it. And this is, go ahead, John. This is oversimplified just to show you the principle. But in this case, we would have dedicated domestic hot water on each of these floors, like we show here. So again, this is assuming that simple application. All right, let's take a look at a 10-floor building. This is multi-story. And if we look down at the bottom and we're coming in at 70 PSI in our mains, let's put a boosting unit in the basement down at floor 0 and boost that pressure up to 95. So here again, we have the domestic hot water source down there in the basement, and we have a riser that goes up through the building. We're going to start off at 95 PSI in the basement. And so on floor 0, we would have 95 PSI. Now we're looking at upstream of the PRV. So these PSI numbers are upstream of the PRVs. And at 95 PSI, we have to have pressure reducing valves for floor 0. So that we would put a PRV in the hot line and in the cold piping to that floor 0 and set those at 45. So on that floor 0, we're going from 95 down to 45. And again, using the principles that John talked about, as we go up to floor 1, 2, 3, 4, and 5, you can see that the pressure on the upstream side of the PRVs is going to drop by 5 PSI until we get all the way up to around floor 8, 9, and 10. And actually the PRVs would be optional up there because you can use that 55 or 50 or 45 PSI directly without reducing it at those higher levels. So again, an illustration of static reduction in pressure as we go up from the basement.
Yeah, and also the recirc.
Yes, right. The recirc here is really nice because it's simple, right? We have a recirc line that taps off all the way up from the top. It's in the riser and coming all the way back down. So that recirc line is, in floor 0, it's at 95 PSI, but that's fine. That's going to work just fine with that indirect storage tank there.
Kevin, question.
Yeah.
Is there ever any situation where it makes sense to run a recirc line through some type of PRV, or do you always want to steer clear of the PRV?
Yeah, you never want to do that. Great question, Mark. We have, by the way, we have more detailed schematics and how and where and when to do recirc when you have PRVs. This is a fundamentals presentation, so we're not going to get into that. That would be a whole nother hour-long webinar, and we might do that later. But you never want to have your recirc through a PRV. It just doesn't work. And contact us if you have questions about that. We can provide you with some schematics and help you with design considerations for those applications. Thanks, Mark. Yeah.
Sure. There was another question on the same slide here, and I'll read it. When does a low-rise building fit the criteria for a high-rise building?
Not sure what they're asking there, but I think if you're looking at high pressures, then it would, be similar to a high-rise. If you have a low-rise building and for some reason you have a booster pump and you're raising the pressure enough to go up multiple floors, then those would be considered to be similar in terms of using PRVs.
Okay.
Keep them coming, Mark. So what's nice about this layout is that you have individual floor level control for your hot and your cold. Okay, that's really nice because you can tweak those set points on those PRVs, but you do have more valves to purchase and maintain compared to other configurations that might use fewer valves. And by the way, these are fundamental schematics. They're very basic. There are a lot of different ways to do this. You can have top feed systems like John showed earlier. You can have more than one mechanical room on different levels, and they would all look a little bit differently schematic wise. But I think you get the idea here with the static pressure changes in elevation. Let's look at one more slide. This one's a little more complicated, a 35 floor building. Now what we have here is a mechanical room on the ground floor, and we have central domestic hot water production, but this time we have a heat exchanger. Why? Because we're boosting up to 220 PSI. So this is going to require a higher pressure mains. That riser is going to be much higher than 95 that we looked at earlier. And we still have recirc though. That same principle of doing recirc in the riser applies here. That's okay to do that. And what we're doing in this application is explained in that square. If you look at each zone, let's take a look at that zone, that box representing the zone. So we're coming in at 220 PSI. Now, John talked about the two-stage pressure reduction. We have to take that 220 down to 90 and then down to 45. So you can't take that 220 directly to 45. That's greater than a 3-to-1, right? So keep that ratio in mind. And in this particular schematic, and again, these can vary, we're using a pair of two-stage PRVs to serve 5 floors. So again, we have the static decrease from 45 to 40 to 35 to 30 to 25. Now, admittedly, that 25 is a little bit low, but we're talking about the principles here. So you could have a pair of PRVs that serves a zone of 5 floors. Okay, just another way to do it. And you'll see in the riser that we have to use two-stage PRVs all the way up to around floor 15, because that's when we're looking at 145 PSI. We still need to take that down in 2 steps, but once we get up to floor 20, that second, that pair of PRVs there is not two-stage pressure reduction, because we can take 120 down to a usable pressure setting without breaking that 3-to-1 reduction ratio rule, okay? And then as we go up there, you'll see also the pressures begin to decline to the point where they would actually be optional way up there on floor 35. So a number of different ways to do it. This is just one way. It's representative of the principles of static pressure. So this is nice because we have zone level control. We have fewer PRVs. So 4 PRVs, 2 sets of 2-stage can serve 5 floors. So it's not too many PRVs, but we have high pressure risers. Okay, now that's fine as long as you design for it, but we do need that heat exchanger down in the domestic hot water production mechanical room. And we do need the 2-stage pressure reduction in those lower zones. And that's actually pretty common to do it this way. Again, just another example of what you can do with PRVs. One downside, if you look again within that zone box, is we have pressures that are different from floor 0 to floor 4. So we have to know, and we have to be able to deal with that because those 5 floors are served with a given set of PRVs. So there's a little bit of give and take everywhere. The more PRVs you have, the better control, the more you can refine pressure control in each area. Let's see, what else can we say about this one? Max or Mark or John, any questions? I think this is my last slide. Again, we just looked at a few basic schematics to get the principles across.
One of the questions on that last slide, and those are just kind of examples that, depending on your project, 25 PSI on a floor may not be enough for your particular fixture set or something, but just kind of as an illustration for how you would cut that down, maybe all those numbers need to be 20 PSI higher, just as a concept. And I'll put the Hydronics link in the chat there too, so you can kind of scroll through a lot of the similar information as you go as well. So if you want, Kevin, I can kind of do the recap, and then there are a couple of questions that we got in the chat that I'll read through too. And we're always interested to hear, how do you do it? Of those applications, do you like to do, a PRV per floor? Do you like to do the groups for high-rise applications? We're always interested to hear for the, as big as North America is, what's popular with your particular plumbing group So feel free to let us know in the chat or follow up with us afterwards. So in summary, stable pressure is critical to prevent system damage. Stable pressure was something that even came up in our building in Milwaukee that we turned up the pressure to do some testing at one point. It was just holding the flush valves and the urinals open. So this is something that comes up all over the place, and it's nice to have the tools to deal with kind of dynamic systems like this. So we talked about elevation. You can just click through all those if you want, Siggy. Piston style PRVs, and again, piston style PRVs are great for those water hammer systems. In the rare cases that you would see a PRV with a rip diaphragm twice in a row, you really should look at something like a PistonType PRV that can better stand up to that water hammer, because there are just more fixtures in the world that have fast close solenoids. Even the faucet that we use for our kitchen sink is a tap on, tap off. That's the type of fixture that wouldn't have been a fast close like that in the past, and is now something that could potentially cause more hammer that could be a good fit for piston style PRVs. Diaphragm PRVs, too much pressure drop, cavitation and noise, and then either in series or in parallel for PRV reduction. So I'll run through the rest of the housekeeping slides, and then I'll read a couple of the questions that we've got here. And all of these are really well kind of recapped in that Hydronics link that I put in the chat. And this team is great at answering these questions too. So if you have a PRV that's making noise, there are a few different types of noise that can be created, and we're really well versed to figure out, is it high flow, low flow, is it dirt, what's causing the issue there. So this is our live tech support team. We also cover a lot of this stuff in our podcast. So the Ask Caleffi podcast is a great resource. We kind of designed it for the contractor driving to the job site, an audio only version of the same information that we're presenting here, right from the tech support guys, Greg and Dan. Then another series that I really like, Cody put together, the 5 things you need to know. Imagine a coffee with Caleffi, but in 5 to 7 minutes. That's kind of what we do with that series. So video to help you see what's going on, but just a little bit shorter time frame. I think it's a great fit for a busy wholesale counter or something as well. And then follow us on social media. We love seeing job site photos. We have our YouTube channel for Coffee with Caleffi and other things like the 5 things, the Ask Caleffi video series, Facebook, Twitter, Instagram. We love to see what you guys are up to. And sometimes we find great photos from the field that we put into the Coffee with Caleffi that we're happy to give you credit for if you tag us in those. Okay, so that takes us to the Q&A piece. Let me find a couple from the chat window here. So one of the questions early on is, why not use a direct acting pilot valve that would eliminate the fall off pressure? So I think that a simple answer would be cost, but do you guys want to kind of cover in maybe a 7-story building why that might or might not be a good selection compared to what we described with the diaphragm and piston style PRVs?
Yeah, go ahead, John.
Yeah, I'm not exactly sure what he means by pilot. There are pilot operated pressure reducing valves. They're fairly complex compared to what we looked at here, but they do have lower fall off pressure situations. So they do exist in the market right now. I don't believe Caleffi offers that in North America. That situation may change.
Yeah, typically the pilot operated PRVs are larger, also like 2-inch, 2.5-inch and up, where you have a small PRV that actually controls a larger valve, actually called a pressure control valve. And they typically have very little or even no fall off, and those are for the larger piping. So typically 1/2 to 2-inch are direct acting PRVs where the fall off is just acceptable. It's just the way they work, but typically larger sizes. And you're right, John, we don't carry those right now in North America.
And then we had a couple questions that relate to booster pumps. So there are a lot of booster pumps on the market with ECM technology that can keep up with the proper pressure regulation. when you get to a bigger building, let's say it's a high rise, there is still some cause in those groups that you showed in kind of that last slide, that maybe you break it up by a few floors to use pressure reducing valves still. Do you want to kind of, there's a lot of gray area, I think, where booster pumps pick up and PRVs take over there, but what's some advice for where to look for that trade-off there?
Yeah, well, I'm not that familiar with the exact control algorithms that those booster pumps, the variable speed ones use, but I'm assuming that they can probably adjust to some degree for varying inlet pressures. For example, in a high-rise building, as you have more and more water flow to fixtures, that is going to change that dynamic pressure drop situation in a portion of that system, and the pressure boosting pump likely has an algorithm that can adapt to that. So if the inlet pressure is varying, it could change its speed and probably maintain a set outlet pressure. But again, that outlet pressure would be high enough, well above the pressure that you'd want to send to fixtures, just above the booster pump. So it doesn't, the use of the variable speed booster pump doesn't eliminate the need for pressure reduction with valves, I should say, pressure reduction valves.
So I've got a question for high pressure, high rise system. Is the heat exchanger always required to handle the higher pressure at the central heating location? And I think that part of that answer would be, where is your central heating location? Is it on the roof, or is it in the basement? Because one of the slides that we showed, I think you would need a 220 plus PSI relief valve on that water heater if there wasn't a heat exchanger there. But do you want to kind of elaborate on that a little bit?
Yeah, it's like you say, depending where it is and what is the heat source, the domestic heat source rated for. I'm thinking, residential, maybe 150 PSI is a typical pressure reducing valve or pressure relief valve setting. So getting into 200 plus PSI, is the water heating device rated for that? And if not, you're going to need separation with a heat exchanger. And to your point, Max, putting it up on the roof, definitely that would change the scenario and possibly eliminate the heat exchanger. So it's really just a pressure dependent situation and a pressure rating on the domestic heat source that would determine whether you need the heat exchanger or not.
And one of the things that's kind of interesting, we don't do a ton of high-rise construction that's over, 35 floors with our product catalog in the US typically. But one of the things that's interesting is, depending on how you break up a tall building, it's just additional versions of what we've showed here. So one of our colleagues who has done some big buildings in Dubai explained that, I don't remember, it's like every 20 floors they had to have 1 or 2 floors of mechanical space in order to get that water and all the other HVAC things all the way up to the top of the building. That even in those buildings that it's a $1 million, 1,000 square foot apartment, you just have to have a lot of space and break that pressure, water pressure system up into a bunch of blocks to go that high. And if you just reduce the amount of floors, it doesn't really change the different approaches that we've showed here at a very simple look. It's just you have to do it more times, really.
Right.
Yep.
And I think that is probably the majority of the questions that have come in, unless anybody else has a question. We've got one, where is Hot Rod? So he'll be back next month to talk about expansion tanks with Cody. So easy answer to that question. Anybody else on the lines have a question that they want to pose to John and Kevin?
Yeah, we with all the experience that we have with the tech support phone calls, Kevin, coming into your group, is there a couple of categories that, in terms of issues, application related to direct acting pressure reducing valves, that we see frequently and could be addressed in this to this audience?
The number one call involves dirt. When someone calls and says, hey, this thing isn't holding pressure, or the pressure is creeping up, or we can't get any flow through this thing. Unfortunately, most of the time they just take it out and put a new one in there, and they send it back to us, and we open it up and it's full of dirt. John showed a picture with the screen clogged up, and that's by far the number one. We haven't had any other common failures like diaphragm issues. Our diaphragms on the diaphragm valves are very rugged. It's dirt or debris or pipe dope or tape or something that gets in there, and that's the problem.
I think you struck a chord with the you don't necessarily size your PRV to the pipe size. You could get into trouble doing that, oversizing or undersizing. So I think most commonly we'd probably see oversizing, where it's thought that okay, I got 1 1/4 inch line coming in here, I'm going to put a 1 1/4 inch pressure reducing valve. Do you run into issues with oversized PRV in applications, and how do you know it's oversized? What are some of the symptoms?
You can actually get noise also from an oversized valve. If you have a valve that's line size and it's trying to control water flow with just one lavatory flowing or something like that, if you get too big of a valve and it's trying to open just a very, very small bit, you can get high-pitched noise from that too. So that we do get that once in a while. I would say undersized also, we get those calls just making a lot of noise, and we'll talk to the contractor and find out, what's the GPM. We really have to, as John said, you really need to know the GPM, the max GPM, and then also the minimum. Our valves can handle generally down to about 1 foot per second of velocity, so that depends on the pipe size. But remember that 3 to 6 feet max flow design band, and you'll usually be fine.
So if your maximum flow rate, your design flow rate, is going to put you into a 1 1/4 inch valve or 2 inch valve or 1 1/2, whatever. But you also have some very small flow demands that might fall underneath the minimum rating for the valve, whether it's Caleffi or anyone else. Is that where you're going to want to put a two in series type two in parallel type application?
Go ahead, John.
Yeah, 2 in parallel. I thought that was a very ingenious solution when you look at how multiple valves in parallel with different settings, how essentially they hand pressure regulation control starting from the smallest valve at the lowest flow rates, and then literally handing off that function to larger valves. We've shown 2 valves, which again, in most applications would probably be sufficient, but the theory can extend to more than 2 valves. You could potentially have 3, even 4 valves in a very, very wide flow rate range application. But yeah, two in parallel would be the typical.
There's a question concerning the selection of the valve itself. You showed an example of, I think it was a 1 inch valve with 100 PSI coming in, and you set the first valve, the smaller valve at 70, right? And the larger valve at 60 because you want it to open up later.
Correct.
Is the if you have much higher flow demands, the ability to select the right size valve, the size of the big one and the small one, how difficult is that, or is that pretty straightforward?
Again, I would just go back looking at the overall range and start at the low end of the range and see which is your smallest valve, and then look at the other end of the range. How big would that valve have to be? And you'd want to have it so that the flow rate ranges, I would think that they would somewhat overlap or come close to overlapping. I don't see, for example, a 1/2 inch valve paired up with a 2 inch valve. That flow rate range just would not overlap. Yeah, it would just be a matter of looking at what's the overall flow rate range, start at the low end, look at the high end, and then see hopefully 2 valves would be sufficient so that those 2 flow rate ranges, the upper end of the small valve and the lower end of the large valve would overlap.
Last question. And maybe I see we're running over the hour. Last question is, you talked about the two different types of valves in the market, direct acting. You have a diaphragm, traditional type of valve, and then you have a piston, a solid unflexible surface between your pressure zones. What's the primary application for that piston type valve again? Is it really extreme conditions, water hammer, pressure variations? Is that one of the applications that this kind of a rugged valve would be used in?
I think higher pressure applications were one, and I believe that irrigation applications, Max mentioned any kind of solenoid water flow control, irrigation systems, or some other type of industrial processes using a solenoid valve. They open and close extremely fast, and I would think that the inertia, the mass of the piston would help attenuate that pressure pulse that would happen when you have a solenoid valve closing rapidly. Kevin,
John, does that include if you have a zoned irrigation system, do you have buried zone valves, basically solenoid valves that are turning on and off? Is that the type of water hammer that could create havoc on a diaphragm type valve? Is that a typical situation you're referring to?
I would think potentially, especially if the pressure ratings, if the pressures that those systems are operating at are high. My understanding is that the piston valve is just more rugged. It's going to handle the higher pressure applications better. So yeah, if you have any kind of zoned irrigation system, or again, it could be processed water going through multiple branches, all under some automatic control system, that the piston valve would hold up better in an application like that than a diaphragm valve would.
Yeah, you're right. The downstream water hammer punishes that diaphragm quite a bit. The diaphragms are very sensitive compared to a piston. And if you have constant hammering downstream, that diaphragm is going to be put through a lot of work. Also, something to remember is the PistonType PRV, we have a high range setting on those. So when you're doing two-stage pressure reduction, the setting is from 95 to 150. So the setting itself allows you to take that first pressure drop. A lot of PRVs that have an adjustment range of 15 to 75, you can't set them to go from 240 to 125, for example. They don't have the set point range to do that.
And what are some of the applications we know of that the pressure, the mains pressure is just too high? Do we travel around and see that regionally? Is it a regional issue?
Hot Rod said when he was in North Carolina that they actually had over 250 PSI coming to the residences from the municipal supply lines, which was really interesting. They go through a lot of PRVs out there because of that.
Is that from a high elevation reservoir with the pressure coming down?
It must be from the mountains, and we were pretty surprised about that. So
how about a water tower? I mean, the water towers are getting big these days. Buildings being serviced by close proximation to the water tower, is that another area that we find?
Yeah, that you could see that. And when we have urban sprawl and neighborhoods get added on to the end of municipal supply lines, in some cases they have to bump up the booster pump pressure at the supply mains. And so those homes near the supply are going to see a pressure increase. They may see high pressures too.
I was down in North Carolina, and there was a community well service servicing, I guess, hundreds of houses in this neighborhood. And it was interesting. It was exactly that, what you just talked about. Even though it's a well, all the homes had to have pressure reducing valves, because to service all of those sprawling homes, pressure had to be boosted up, which caused pressure closer to those boosters to be extremely high. So even those type of applications are opportunities for PRVs to control pressure. I ran out of questions.
Well, is Max still there?
Yeah, we can kind of wrap it up here. And I mean, I think to the point of this conversation, if your municipality is sending 300 PSI water to your house, they probably need to fix that. But if they can't, we're here to help, I guess. So I wanted to say thanks to John Siegenthaler and to Kevin for walking us through this topic. This is definitely something we will revisit with kind of a 2.0, a little bit more advanced version at some point. There are a lot of questions that kind of go into that realm. We just wanted to start with the fundamentals today. But thank you for attending, and we'll see you next time.
Thank you, Max.